Hey folks, my name is Nathan Johnston. Welcome to Lecture 9 of Vector Calculus, which is all about scalar line integrals. And this is actually going to be the first of two lectures on scalar line integrals. Today, what we're going to be talking about is, first off, what is a scalar line integral? Like, what's it trying to do, or what does it represent? And then secondly, how do we actually compute it? Okay, like how do you come up with a numerical value for the scalar line integral? Okay, so let's start off with what is it? What's it trying to do? Okay, so the idea, the setup behind a scalar line integral is you've got two things. So first off, you've got a scalar field. And remember from last class, what a scalar field does is it assigns numerical values to each point in space. So in the example here, space is two-dimensional space, it's R2, and we've got a numerical value assigned to each point in R2. Okay, and then we've also got a curve or a path tracing out a curve in that same space, in R2 in this example. Okay, and what a scalar line integral is it's what you get if you accumulate values from the scalar field along this curve, okay? And what I mean by that, like what do I mean by accumulating values? And okay, sort of speaking a little bit roughly, but hopefully trying to relate this to things you already know. What I mean here by accumulating values is exactly what I would mean if I said that an integral accumulates values. Like think back to functions of one variable. You already know how to integrate these. Remember, if you got a function g from r to r, a function of one variable, when you integrate it, what you're doing is you're accumulating values of g of x as x ranges from a to b. In other words, like x, the input is increasing from a to b, and you're kind of doing a continuous sum of all the values of g of x in that interval. Except when you're adding them up, of course, you can't just add them up. There's infinitely many of them. You're going to get infinity if you just add them up. So you've got to sort of proportionally scale them. Okay, you've got to sort of like add up the values, but scaled appropriately so that the sum actually makes sense. That's what I mean by accumulating values of something. So here, when I say accumulate values of the scalar field, it's like, okay, down here, the value of the scalar field is, I don't know, maybe 41 or 42. Up here, it's a little bit higher, it's 45. And then you imagine sort of adding up tiny little pieces of those numbers, but weighted according to like how long the curve is in the region of space where the value is that number. Okay, so how could we actually compute this? And we're going to talk about that. What we're going to do today is we're going to derive a formula for this. But before we do that, I want to show you one thing that we're not doing, okay? I want to talk about one thing that is not a scalar line integral, okay? And that is something like this. For example, suppose that the scalar field was representing temperature, okay? So the scalar field tells me how hot it is at different points in space. And my path is like a car driving through space, okay? Maybe like it's R2 and the car is driving on the surface of the Earth or something like that, okay? If I wanted to know, for example, what is the average temperature of the car as it drives along some curve, as it follows this path, that actually isn't a scalar line integral for reasons that I'll get to. So let's talk about how to compute this, and we'll talk about why it's not what I'm talking about in a second, okay? So how would I compute this, okay? The car is driving through a scalar field, and I want to compute what is the average temperature that that car sees. Okay, well, what I could do is I could just turn this into an intro calc problem. I could turn this into a function of one variable and just integrate it, right? If my path, so that's going from one-dimensional space to two-dimensional space, if that's representing position, and then my scalar field from two-dimensional space to one-dimensional space, that's representing temperature, then when I compose them, f composed with x, that's just a function from one-dimensional space to one-dimensional space now. And what that function does is it skips out the middleman. It just doesn't care about the x and y coordinates. It just goes directly from, what is the time to what is the temperature. It takes in time, spits out temperature. And that's a function of one variable. And to compute the average temperature, average with respect to time, you would just integrate that function and divide by the width of the time interval. Okay, you would take the difference of the last time minus the first time and just sort of scale the integral appropriately by that amount. And that would give you the average temperature that the car sees on its trip. And again, this is not a scalar line integral, but it's still sort of instructive. So I still want to go through it first. And then we'll talk about, okay, why is it not a scalar line integral and how do we have to tweak it to make it one? Okay, so let's go through an actual computational example of something like this. Okay, so suppose that a car, it's driving along the path from negative 4/3 to 4/3, defined in this way. Okay, so the x-coordinate is t cubed, the y-coordinate is t to the power 5 minus t, and suppose furthermore that the air temperature at the position xy in degrees Fahrenheit, it's given by this function here. So x squared plus y squared minus 5xy plus 50. Our goal is to do exactly what we've been talking about, okay? Compute the average air temperature encountered by the car as it drives. In other words, imagine someone hanging out the window of the car as it drives, and they take 1 billion temperature measurements as they're driving along, and then they average together those 1 billion temperature measurements. What are they going to get? Okay, so how do we do this? Well, we need to figure out what's our scalar field and what's our path. Well, our scalar field is exactly this temperature function, right? This is a function from R2 to R, scalar field, yay. This is our path. What we've got to do is we've got to compose them together, okay? So plug the path x of t into the temperature function. So in this temperature function, in other words, everywhere I see an x, I replace it by t cubed because that's the x component of the path. And everywhere I see y, I replace it by t to the power 5 minus t because that's the y component. Okay, so I get this expression here as my direct from time to temperature function, okay, as my composite function. And all I'm going to do is I'm going to expand that out, okay? And yay, it's just a polynomial. Okay, what I'm going to do now is I'm going to integrate that and divide by the width of the time interval, okay? And that'll give me the average temperature then. Okay, so I do that. Okay, I integrate this function here that I'm integrating is exactly the f of x of t that I saw up above, and I divide by the width of the time interval, okay, which is just going to be 8/3. I'm dividing by 8/3. And I mean, it's ugly here because this is a high degree polynomial. I'm plugging ugly rational numbers into it, but I mean, it's just sort of a straightforward calculation. Despite how ugly it is, plug things into a calculator, and you're going to get this ridiculous fraction here as your answer, or approximately 49.02 degrees Fahrenheit. Okay, so fine, that's the answer to the problem. That's true. I'm claiming this is not a scalar line integral, okay? And to try to convince you of like, okay, like what's different here between like this perfectly valid problem and actually what I want a scalar line integral to be, let's look at sort of the plot of what's going on here, okay? So in the plot here, you can see the car driving along some path, and it's sort of like you're averaging out all the temperatures that it sees as it drives along this path. Now, the thing about this path is you'll notice that sort of near the edges of the path, the car is going quite quickly, and in the middle of the path where it's doing that almost S-shaped bend, it's traveling quite slowly, okay? So if you're averaging with respect to time, like we did in this calculation, then what's going to happen is when you're averaging over time, you're sort of accumulating more of the temperature measurements in the middle near t equals 0 where the car is going slow, because more like if you imagine someone hanging out the window taking temperature measurements as they drive, they're taking more temperature measurements in the region near the origin because the car's going slower there. They're averaging with respect to time. And that's what makes it not a scalar line integral, okay? So if you want to average with respect to time, just do what we did. Compose the two functions. It's an intro calculus problem. If instead you want to average with respect to length, arc length, now it's going to be a scalar line integral, okay? That's the difference. What a scalar line integral is it's an accumulation of scalar field values with respect to arc length, not with respect to time. In other words, it's a path independent thing, okay? It only depends on the curve, not how the particle is driving or moving along that curve. Okay, so how could we possibly actually compute this thing? And here's the trick. How we're going to define this precisely is we're going to say, okay, a scalar line integral, it's exactly what we just did, okay? You just integrate the composition of the two functions, except to make it with respect to arc length instead of with respect to time, you just have to make sure that the parameterization you're using is a parameterization with respect to arc length, okay? So you've got whatever your curve is, you want to integrate it, find a parameterization with respect to arc length, and integrate the composition of the scalar field with that. And that's what a scalar line integral is, okay? So here's the setup a little bit more formally, just to pin things down, okay? Suppose that you've got some domain of a scalar field, okay? So F is our scalar field. It's going from some region in space down to the scalars, okay? And you've got some curve that's living inside that domain, okay? And what we need here, like the reason we need C inside of X, the reason we need C, the curve inside of the domain, is so that the scalar field is actually defined on C, so that when the particle moves around C and we accumulate these values, there are values to accumulate. Okay, and then what we do is we say, no, we can't just use any parameterization. We can't use any path. We've got to use a parameterization by arc length. But if we have one of those, then great. The scalar line integral of the curve, this is a path, like a path independent quantity. It depends on the curve. What it is, well, okay, this chunk on the left, this is just the notation that we're using for scalar line integral. It's the integral over the curve C of the scalar field with respect to arc length, okay? That's what this dl means here. Like if you do an integral dx, that means like you're accumulating values in the x direction. Okay, dl means I'm accumulating values per piece of length, of arc length of the curve. Okay, so this over here, this is just our notation for scalar line integral. This thing over here is, at least in principle, how you would compute it. What you do is exactly what we did up above. Compose the scalar field with the path, and then just integrate it with respect to whatever the parameter is. It's L here, okay, when you got a parameterization by arc length. L is T for parameterizations by arc length, so it's the same thing. Fine and dandy. This works as a definition of the scalar line integral. It doesn't help us actually compute it. Because remember, parameterizations by arc length, those are awful to compute in practice. Okay, so how can we get around this? Okay, and it's very similar to actually how we got around this problem when we were trying to define and compute curvature last week. Okay, what you do is just do a change of variables in the integration. Okay, so what I'm going to do is I'm going to say, okay, suppose I've got just any parameterization of the curve now, and I would like a way of computing the scalar line integral directly from that. I want a formula that just involves x and things I can compute from x. Okay, what you do is you say, okay, great. If x tilde, if my parameterization by arc length is derived from x, then remember it's going to look something like this. When we computed parameterization by arc length back in the day, what we did was we got L in terms of t, arc length in terms of time, inverted it so it was t in terms of L, and plugged that into the original path. So this was our formula for going from just any path to a parameterization by arc length. Okay, and now what we can do is we can just say, okay, I'm not going to have x tilde up here. Instead, I'm just going to have x of t of L. Okay, and I'll just do suitable change of variable stuff and see what pops out of it. Okay, so let's do that. Okay, well, here, my scalar line integral, just by definition, is this. Okay, so that first equality right there, it's just the definitional equality. This is what a scalar line integral is. Okay, next up, what do? I say, okay, x tilde, great. That's just x of t of L. Okay, so I'm just going to plop that in there. It's still dl, and these bounds on the integral are still as little l goes from 0 to big L. Okay, and then basically my last step, like the key thing that actually turns this into something that I can actually compute, is now I do my change of variables for integrals. Okay, so this, back in Calc 1, whenever you're learning how to do integration, this sometimes is called U substitution or chain rule in reverse. That's all I'm doing here is I'm saying, no, I don't want to do an integral with respect to L. I want to do an integral with respect to T, the parameter of the path that's easier to work with and come up with. Okay, so what I'm going to do is, how do I change it to an integral with respect to t? Well, just to introduce a dl by dt on the inside, okay? And sort of like the heuristic, or the way to remember this, is, oh, the dt's just cancel, and I get dl back again, okay? Really, it's the chain rule that makes this work, but that's sort of how you can think about it. Okay, and now, well, dl by dt, how do I compute that? Well, remember, arc length, that's just, the integral of the original path. So then, like, dl by dt, that was the speed of the path. Okay, so this was something that we saw, I don't know, several lectures ago at this point. dl by dt, it's just the speed of the path. It's the length of the velocity vector. Okay, so how can we compute a scalar line integral? Well, this is the formula right here. You compose the two functions just like we did in that first average temperature example, but then you need sort of this correction factor here, the speed of the path, to sort of account for the fact that, like, you don't actually want to take time into account. You don't want the speed of the particle to affect your final answer. And this is the correction factor that you need to make that work. And the way you can think about this is, let's suppose, imagine the particle is going very, very fast. The speed is large. Then as you're taking temperature measurements, you're taking fewer of them per unit of distance, right? So they're sort of affecting things less. Well, this correction factor makes it so that they don't affect things less. When the speed is high, this brings things back up proportionally to where they should be, so that now it's per unit of arc length instead. Okay, so anyway, let's throw this all into a theorem box, and then we'll be done. And then next lecture video, what we're going to do is we're actually going to use this and compute some things with it. Okay, so this is our final observation for the video. Suppose, again, you've got some domain, okay, your scalar field is defined on that domain, and you've got some curve in that domain so that the scalar field is defined on it. Then the way you can compute the scalar line integral, okay, definitional notation for it is this quantity, and this is exactly the formula that we wrote down on the previous slide. All right, and that's it for today, everyone. Thanks for watching. I'll see you next class when we do a bunch of computational examples.